Okay, welcome to the 30th class meeting of EECE574, the graduate level probability and random processes. I've decided not to give you the homework 15, so happy. And final exam will be again a take-home exam for 48 hours. So on Monday, 11 a.m., the problems will be available from the PLMS. And you have to upload your solutions in 48 hours. Okay, here goes the overview. We almost finished it, the temporal characterization or characteristics of a random process. And today we are going to study spectral characteristics or frequency domain characterization of a random process. So here goes the review. I spend a lot of time to let you fully understand what really matters, not just the terminology of ergodicity. What really matters is that in many modeling of random process, many modeling of real world time function with uncertainty, we model it as a random process that spans from negative infinity to positive infinity, or in an engineering term, for sufficiently past and for sufficiently sufficient future, something like that. But mathematically speaking, what we are given in reality or in precise mathematical model is a single sample path. So as I repeatedly emphasized throughout this course, if we observe only once, then probabilistic approach may not give us something good, because probability, as now you know, is related to the expectation of an indicator function properly defined. And indicator, the expectation is actually what? Is related to or motivated by the fact that we can observe many times, probably independent and identically, and our arithmetic mean, which means the relative frequency, is close to the ensemble average. So probability theory itself is based on our belief that somehow we can replace the statistical average with ensemble average, or in the area of random process, the time average. So what is important is what? Not the ergodicity, but the is it possible, this question, is it possible for us to estimate something, or in a more larger term, can we make a statistical inference based on a single sample path observation? Got it? So ergodicity in a wide sense, which may not be termed as ergodicity by many others, is that the example is like this. For example, given a Poisson random process, single realization of a sample path, can we fully characterize this Poisson random process? And the answer is yes, because the Poisson counting process is fully characterized by a single scala that is the arrival rate. And the arrival rate can be accurately, very, very accurately estimatable from a single sample path as far as we observe the entire realization, or sufficiently large for a sufficiently large interval. So please remember that what matters is the estimation, or in general, statistical inference. Got it? So remember Poisson counting process as a kind of example for you to understand. However, in general, people just say that ergodicity is about the capability under certain conditions that the statistical average can be replaced by time average. And in that sense, as I emphasized today, and also in the last class meeting, the ergodicity is very similar to the law of large numbers, especially if you think about some discrete time random process whose entries, whose terms are IID random variables. Then your arithmetic mean that appears in your any kind of law of large numbers is actually the time average of a random process. So law of large numbers and ergodicity are closely also related. Of course, ergodicity is, I believe, can be said that a generalized definition from law of large numbers. So ergodicity is much general. Got it? Anyway, as I just told you, the ergodicity is about the replaceability of ensemble average with time average. And we are interested in, for example, this ensemble average or that ensemble average. Or if we have more than one random processes, then we may be interested in something like this, the cross correlation. Or we can even generalize this idea, ergodicity, to a vector valued random process. In that case, you may just simply put under score line, underline, to mean that each random variable is a vector valued, and you may want to replace this Hermitian this conjugation to Hermitian transposition. In that case, your autocorrelation is a matrix valued function of t and tau in general, and your cross correlation is also something similar. Of course, for complex valued random process, you can define complementary or pseudo autocorrelation and pseudo cross correlation. Of course, we can define covariance functions. And given these ensemble averages, we have corresponding what? Corresponding time averages. So the first thing will be the time average of a random process. And second one would be time average of the product of x sampled at t plus tau and x sampled at t. Similarly, we have two random processes, and we calculate the time average of kind of cross correlation. Now, what is the ergodic assumption? What is the definition? We say that they are equal. But given our problem of interest, sometimes we may just need the first equality. The random process has statistical average, same as the time average. Sometimes we need 1 and 2, not only the mean function, but also the autocorrelation function. We want to be ergodic, something like that. And there are many, not only the second order moment, but any nth order moment we may think about, right? But we are not going to cover every possible ergodicity. Let's focus on just first two. And in this case, if this is assumed, we say that we assume that x of t is mean ergodic. Got it? Mean ergodic. And if we assume the second one, we usually say that the random process is assumed to be autocorrelation ergodic. The problem is that the left-hand side is in general a function of t, which is a deterministic function, and the right-hand side is what? Is a random variable. So in order for them to be equal, there is only one possibility. What? The mean is not a function, but a constant for all t. The random variable has, for example, variance 0, so that with probability 1 or in some other sense, you observe only one thing. Now, you know that this right-hand side is related to the limit of a sequence of random variables. So whenever we talk about some limit of something equals something scalar, we have to talk about the mode of convergence of a sequence of random variables. So for this equality, there could be almost sure ergodicity in probability ergodicity, in distribution ergodicity, in the Pitts-mean ergodicity. Among them, we just, in order, just for the educational purpose and also practical reason, we just considered mean square sense convergence. So that's why we studied mean square ergodic in the mean function, mean square ergodic in the autocorrelation function, something like that. Got it? And here goes some interesting lemma related to the mean ergodicity in the mean square sense. So this first thing, and here equality is mean square sense. What does that mean? The right-hand side, when you take the limit, you have to use L dot I dot M to mean limit in the mean, and you have 1 over 2t, and integration interval is length 2t, and you have x of t dt. And here goes t infinity. And you say this is same as the mean function for all t. So this is the mean square ergodicity in the mean function over random process x of t. Now, this is just assumption, or you may say that definition. And what would be the related properties? Some lemmas, theorems, corollaries, something like that. Among them, one of the famous lemma related to the mean ergodic in the mean square sense is this one. So x of t is, the lemma set assumes that x of t is at least y and stationary. And they talk about covariance function and say that this x of t is mean square ergodic in the mean if and only if what? The covariance function, autocovariance function as a function of tau, when it is windowed by a triangular pulse. So we have something like this. And then, of course, we may integrate over this interval so that this really becomes the equivalently the triangular pulse that ranges from negative infinity to positive infinity, and the tau. And we need to divide by 1 of t. If this goes to 0, okay, then if and only if x of t is mean square ergodic in the mean. Of course, this part can be relaxed, so sometimes we relax in this way. Or sometimes we further relax. So if the covariance function is absolutely integrable, then if you divide by 2t and let it tend to infinity, it is always 0. So something like this. So these are kind of corollaries. Sometimes you use this one to show that the random process is mean square ergodic in the mean. Sometimes we use this condition, or sometimes we use the original necessary and sufficient condition. Got it? And also, we talk about autocorrelation ergodicity and joint ergodicity, and something interesting, the ergodic in distribution. And you may have some confusion. I understand. When I first saw it from a populist book, it was very, very confusing. But the idea is very simple. We just define like this. So definition is simple. The autocorrelation function can be replaced by what? The corresponding time autocorrelation function. The ergodic in the distribution over first order CDF is somewhat strange. What was that? We used we considered some so what is the, recall that what is the CDF by definition of a random variable? Probability of the event that capital X less than or equal to X. How can you replace this CDF by using expectation of a function of random variable X? We introduce what? When this event occurs, we have indication. So 1, right? And what? We'd better not say this. We'd better say that U of X minus capital X. And we take the expectation. First, simplify if you got confused, right? For example, I give you a random process problem in the final exam, and you don't understand what does that mean. Then just construct yourself a simplified version of the problem in terms just of random variables, for example, not random process at all. Then you solve the problem, which I didn't give you, but you learn something. And based on the lesson of that experience, you may be able to solve a more complicated problem. So anyway, the CDF of a random variable can be written in this way. Let's see why this is true. Every expectation is what? Summation or integration of the value times probability. So let's say that, okay, let me use just integration. Now, what is the value? U of X minus, well, I have a variable. So let me use Y instead of X. And density of X, but let me use the parameter Y. Okay, understand? Right? You have to replace this random variable with some integration variable when you compute. I just used Y, okay, because X is already here. Now, what is that? As a function of Y, this U of X minus Y is what? Is 1 when X is greater than or equal to Y, right? So this is 1 if X is greater than or equal to Y. Means that if this is the value X, right? Then these Y's are less. So you have something like this. What if they are equal? We assumed to include that, right? So we have some function like this. Now we multiply the density of X and integrate. Then what does that mean? Our integration interval becomes negative infinity to X, and you have the density of X, which is what? Probability of event that X is less than or equal to lowercase x. Got it? So let me use different color so that you have less confusion. Got it? So based on this kind of simplification, which now you have that simplification and visualization in your toolbox, right? We go back to this ergodic in the first order CDF of the random process. So what do? We have something like this. Instead of X, we just put X of t. Then what happens? Expectation of U, X minus X of t. What would be that? Simple. Just go back to this one, right? Instead of X, you use X of t, which means that this is probability of event that random process X of t less than or equal to some value x. What is that? By definition, is the first order CDF of the random process. Got it? That appeared in the Kolmogorov's theorem, right? In order to talk about the Kolmogorov's theorem, we defined first order CDF, second order CDF, nth order CDF of a random process x of t, right? So now we want to talk about ergodic random process that is ergodic in the first order CDF, or simply ergodic in distribution. Of course, you can generalize this idea like second order ergodic, third order ergodic, nth order ergodic, right? Depending on your need. If you need to compute joint CDF of a random process, then probably you want to check whether your ergodicity in the second order CDF makes sense or not, right? In that case, what? First, you think about that object and replace or find the corresponding ensemble average. And eventually, what do? You replace this one with corresponding time average. So what is the corresponding time average? So here goes the definition of ergodic in the first order CDF. If x of t is ergodic in the first order CDF, if time average of u of x minus capital X of t equals this one, probably for all x, right? Because the left-hand side is not a single number, it's a function of x. Right-hand side is a function of x, right? So if they are equal for every x, or for almost every x of your almost every x in the region of your interest, then you are done. Okay, so this is the definition. Now, how can you check whether your assumption is really good or not? You use the lemma, right? So you find the corresponding covariance function, or you estimate the corresponding covariance function, right? Because we do not know, we do not know the first order CDF, right? We just assume that we can estimate it from the time average. However, there is no base. So your boss or you yourself may ask, is this assumption really true? In that case, you use the lemma. So what you do is that you estimate the corresponding covariance function and check whether your covariance function satisfies this necessary and sufficient condition. Probably you need to change this one to the corresponding covariance function. But anyway, something like that. Got it? That is the idea. Now, the final question would be, how can we estimate the covariance function given a single sample path? Last time I didn't fully motivate why had we had that last section entitled measurement of correlation functions. Now here it goes, right? You assumed ergodicity, but that does not justify your assumption. But you know that from the lemma, ergodic if and only if covariance function satisfies some condition. So at least by using this lemma, you can check whether your assumption is totally wrong or not. Of course, we never know this covariance function. So even though our test does not justify our assumption, but if it is totally violated, then we can say that, okay, I cannot assume ergodicity. So let's see. So the idea is very simple, and last time I already told you. So in order to calculate, in this case, just correlation function, okay? Covariance is a kind of correlation function, so you can always estimate. The simplest thing is this one. Just you have your observation, single sample path, and delay it right? By tau, and then integrate and divide by the integration interval. That's all. So you very crudely estimate the covariance function or correlation function. And if that correlation function, that estimated correlation function, violates that lemma, how can you assume your ergodicity of the random process? So at least this estimated correlation or covariance function must closely satisfy. That is also difficult, your necessary and sufficient condition. Okay, that's all for chapter 6. Now, let's move on to chapter 7, and I have around 45 minutes. We have 7 sections, and I will do my best, but in case I cannot cover all, what I have found is that fortunately, some of the materials are covered in my previous class meetings, the previous year lectures, so you can find it, but I will do my best. So here goes the motivation. So far, we characterized a random process in the time domain, right? And what was the most important thing? The full characterization always, now you have taken my course, and it's almost the end of the semester, so you must draw this one first, right? So sample space, event space, probability measure. So this is a random experiment modeled by the probability space, and here goes S. And what? The random process was simply a mapping rule parameterized by 2 parameters. One is S, and the other is time index T. Time index T could be an element of a continuum real number, for example, or an element of the natural numbers or element of integers. But anyway, so we simply call or denote the output of this random process as x of t, right? Now, from this one, we defined what? How did you fully characterize? The alternative characterization was done by Kolmogorov's idea. And Kolmogorov's idea is what? Handle each one sampled at some specific time instant as a random value. So this is 1, and 2 is that, okay, first order CDF, second order CDF, blah, 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 must be what? Must be consistent, right? They must be they all exist, and they must be consistent, right? Anyway, what are the partial characterization in the time domain? You may think about the expectation. You may think about autocorrelation function, blah, blah, blah. So these are time domain characterizations, right? Now, what would be the corresponding frequency domain characterization? And when I first saw this chapter, I just believed that this chapter must be very short. Why? Because if we Fourier transform each sample path, then what? This is actually wrong, right? What I thought was this. Okay. Here, instead of the sample path, let me consider its Fourier transform. Let me call this is the Fourier transform of XTS, right? So what? Here, our mapping rule just had time parameter, and here, frequency parameter. And I believe that, okay, I'm done, I'm happy. And unfortunately, my professor didn't explain why this logic was wrong. He just said that, okay, we don't do that without reason, and say that, okay, full characterization in the frequency domain of a random process is difficult. So we just do partial characterization. something was wrong to me. I thought this would work. And when I become a graduate student, almost the same thing happened in the graduate course of the probability and random process. But eventually, I got to know that this equality is problematic because what? Given a function, its continuous time Fourier transform may not exist. We need some conditions for the Fourier transform to exist. Unfortunately, in many applications, the condition is not met by many sample paths. For example, given a random process, you have a collection, ensemble of deterministic functions, sample paths. Some of them, for example, allows Fourier transform, but the others does not. Then can you do this characterization? No, right? Sometimes almost every sample path does not allow Fourier transform or discrete time Fourier transform or continuous time Fourier transform. Then you can't do this. However, in some specific cases, you can do that. This is perfectly good. Okay, so never think this is not allowed. This is allowed in many cases, actually. Right? So just check whether your attempt to use Fourier transform is okay or not. If it's okay, do that, right? Do that, no problem. Got it? One of the reasons why our undergraduate textbook by Peebles, Professor Peebles, didn't put much attention to that example is because he was a radar engineering professor. And as a physical layer communication engineer, usually we, at that time or in the simple random process application, we just wanted to model additive white Gaussian noise. We just wanted to model a digitally modulated signal. There are two approaches, of course. In some information theoretic modeling, we assume that a finite number of symbols is transmitted during almost a finite duration. But that length is large, something like that. Shannon assumed that. And as I told you, if the interval is large enough, for mathematical simplicity, we assume what? That random process ranges from t equals negative infinity to t equals positive infinity. In that case, what will happen? The sample path has infinite energy, right? For example, consider BPSK signal. Continuous forever. What is the energy of that? If you square it and integrate, it blows up, right? That kind of signal, that kind of simple sample path does not allow Fourier transform. So let's review what must have been, what should have been taught when you took signals and systems on a course. Of course, there is no course like that in Korea, I believe. No Seoul National KAIST, no postdoc ever offered signals and systems on a course. That's pity. Okay. Interestingly, if you go to the universities in the US, they have honor courses. Not every, but they have calculus honor courses. Of course, we have calculus honor courses, but something like that. So one of my dream is that I teach signals and systems honor course before I retire in postdoc, but that will never happen. Anyway, so we need some measure theory or some functional analysis stuff. So the first question is this: when can we Fourier transform a deterministic signal? Okay, so let's simplify and consider a Fourier transformation of a deterministic signal because each sample path is anyway a deterministic signal. And if you remember the definition of the Fourier transform, and if you read some advanced calculus or introductory real analysis books, Fourier transform exists if and only if the signal is absolutely integrable. So you take absolute value of the function and integrate from negative infinity to positive infinity. And if it is bounded above, which means that there is some finite number exists and your integration is less than that or less than or equal to that. So this is the, by definition, if x of t satisfies this one, we say that x of t is an L1 function. Actually, L1 is a set of functions. So here is the set of all x of t. Then here is an L1 set. And a function is a member of that set means what? It's absolutely integrable. Now, as an engineer, you want to generalize that one or have some parallel to that. Second one is square integrability. So we take the absolute value and raise to the power of 2 and then integrate. And if that value is finite, then we call the signal is L2. Got it? So here is another one. The reason why I say I draw this L1 and L2 having just intersection without inclusion is that we can easily give us example where signal is L1 but not L2. Signal is L2 but not L1 by using this strange thing, 1 over t raised power of p and limited to 0 to 1 or 1 to infinity, something like that. You know that, right? So by changing the p value between the reason 0, 1 and greater than 1 infinity, then you can sometimes show that a signal which is L1 but not L2, the signal is L2 but not L1, something like that. Okay? And now here is some strange thing, which is what? Signal is a finite power signal. But be careful. Many books define that. By the way, this is denoted by E sub xx. X energy of x, right? The reason why we have two x's is that we want to later write it this way and may consider cross energy defined as what? X of t times y conjugate dt. Got it? Anyway, so here goes the third one. The power over deterministic signal. And here comes what? Your familiar time average. So what is this one? This is time average of instantaneous power of x, right? If this is finite and greater than 0, then it is called a power signal. By the way, L2 is called energy signal. Set of energy signals, which means finite energy signals. Got it? And of course, if a signal is an energy signal, it cannot be a power signal. So this intersection is empty set, but it's very difficult to draw. I just drop it. Got it? So if a signal is an energy signal, its power is 0, so it cannot be a power signal. But I just, for convenience, draw this Venn diagram. And if a signal is a power signal, its energy is infinity. So no intersection. But interestingly, there is a signal. It has infinite energy, infinite power. For example, e to the negative t. If you just calculate absolute value and integral, it blows up. If you square, it blows up. If you square and divide by 1 over 2t, your denominator linearly increases, but your numerator exponentially increases. So it has infinite power. So there are many signals outside, right? Anyway, here, what you want to remember is this one. Fourier transform, its precise definition is related to the L1 set. The problem is that there are many signals of our engineering interest that is not in this L1 set. For example, cosine signal. It's a power signal, right? If you integrate, it blows up to infinity. So as I told you, this is empty, this is empty. Got it? Yeah. By definition. Yeah. And your friendly sync pulse, right? If you calculate this one, it blows up because 1 over t, if you integrate, it blows up. Something like that. Then what is the use of Fourier transform if many signals of interest that does not have the Fourier transform? And there is another problem. Sometimes your Fourier transform is okay because signal is L1 signal. However, your signal, a Fourier transform is not L1. Your signal is L1, but your Fourier transform is not L1, which means that inverse Fourier transform does not exist. In that case, Fourier transform does not mean much. And there are many signals like that. So what can we do? Then here comes not well known, but very important relaxation of the definition. That is so-called Fourier planchural transform. So here goes the relaxation. Instead of here, see that this typo. Here you have just direct integration, but here Fourier planchural transform has something similar to time average, but there is no 1 over 2t. Okay, you take a finite interval. So you do not just directly compute the integration from negative infinity to positive infinity. You take a chunk of it, and you calculate the integral. And then you increase t, the interval length. And if that sequence of numbers converges to a number, has the limit, then we call that limit as what? The Fourier planchural transform of the signal evaluated as specific f. So this Fourier planchural transform, we hope to exist for all t. And one good thing is that if the signal is L2, then this exists. Okay? So signal is an energy signal. Fourier planchural transform exists. One more thing better, if signal is an energy signal, its Fourier transform is also an energy signal. So its inverse transform exists. Great, right? Another thing, if signal is L1 and L2, then what happens? Your Fourier planchural transform equals, in some sense, your Fourier transform. Got it? So in many signal gen systems undergraduate textbook, even though they are actually talking about Fourier planchural transform, they just say Fourier transform. Why? They do not want to ward off their undergraduate student. In most of the US universities, your department is not restricted. As far as you are, for example, entered to the College of Engineering, you can choose any major. And if your first mandatory course teaches too much, everyone will flee away, right? So they do not put this material in no signal gen systems text. Fourier transform is already headache to most of the students, but they do not want to say that, okay, this is important, but only for L1. What is L1? And something like that. So they don't say. But I hope you know this. Got it? So I will also just say that Fourier transform, even though I'm doing Fourier planchural transform. Got it? So here goes Parseval's theorem or relation. And cross energy, as I already told you, and it reduces to the energy if x equals y, can be what? Can be computed in terms of the Fourier planchural transforms of x and y. This is an amazing idea because the simplest case of x equals y, see that? the energy of the signal can be computed by integrating this instantaneous power. And here on the frequency domain, what? Your absolute square of the Fourier transform serves almost the same role as instantaneous power. And now this is a function of time. So what? Energy at kind of this contribution of the signal at to the energy at time t, and you accumulate to have that energy. Now in the frequency domain, you have the contribution of the Fourier transform to the energy at specific frequency. Now you integrate this frequency function and get an energy. What do you want to call this one? It's an energy spectrum or energy spectral density. And you may say that, wait a minute, this is not good. Even though I sum up and have something, I cannot always say that this is an energy density. You are right. So here goes linear filtering. So h of t is a linear filter, possibly bandpass. Now, you know from signal gen systems, output Fourier transform is simply the product between the Fourier transforms of the input and the impulse, the LTI system. Now, let's compute the output energy. Then you have this, right? Now, let's consider a very narrow bandpass filter, h of f. Then what does that mean? This energy is the filtered version of the signal at that specific frequency. And that really means the contribution of the signal at that frequency to the total energy. What is that? That is x of f evaluated at a specific value. So really, this absolute value square of x of tf can be interpreted as the energy spectral density, because it really means the portion of energy at specific frequency. Got it? The reason why I talk about this is that this exactly parallel ideas comes when we study the power spectral density of a random process. Anyway, so let's think about the frequency domain characterization of a random process. And as I already told you, if the sample paths are all Fourier transformable, then we are happy. But unfortunately, not many random processes allow that. Of course, if this exists, then we can do partial characterization by computing some expectation mean path of the Fourier transform. We may compute the autocorrelation of Fourier transform of sample paths, right? No problem if they exist. Unfortunately, existence is not guaranteed in many important applications. So that's why this approach is not taught. However, remember, this may be allowed your specific application. In that case, just use it. Anyway, our focus is a partial characterization in the frequency domain by using the power spectrum. And let's see, what is that? So here goes the new notation, which is different from Peebles' book. Actually, Peebles' book does not have the major theoretic flavor, so he never used parenthesis S. But as a graduate course, we need that. The problem is that if I use T and frequency F in the inside the parentheses, there are too many parameters. So I decided to change. So I spent more than 2 hours last night to change that. So suppose this is a specific sample path from your ensemble. Now, its time-limited version is denoted by x sub s of t with superscript t. So this parenthesis superscript means what? How you truncate in the time domain. See that truncation occurs in the time domain to your sample path. Got it? Now, your truncated signal in most of the applications will become what? finite energy signal, right? There is no engineering sense infinite energy signal during finite period, right? Energy is finite anyway. So now you can think about Fourier transform of this truncated signal, which denoted by x sub f of s, but with superscript t to mean that, hey, this is the Fourier transform, but after time domain truncation. So now this exists, no problem. And we do Fourier transform. Be careful. Here, by definition, x sub f sub t of s. This s means what? The specific sample path for the outcome s, right? And this is simply Fourier transform of time function. And here goes the trick. We can drop this superscript by limiting the integration interval to negative t to positive t, right? See that? Here we have superscript. Here we don't have superscript. We have infinite interval. We have finite interval. Got it? Now, what is the energy contained in x of t on that finite duration? Using the Parseval's relation, we have what? This is time domain computation of the energy using the truncated signal. Or we may drop this one and limit the integration interval like this. And we may have some frequency domain representation, right? Be careful. What is it? It's a function of s. Means that this is a random variable. So given a sample path, right? So given a random process, if we truncate and compute the energy, it's a random variable yet, right? Now, what is the power? Power is simple. Power of the truncated signal is what? Energy divided by its interval. So here we assume the length of interval is 2 capital T. So our power, which is again a random variable because it's a function of s, right? But you can compute it in the time domain or in the frequency domain by using the Parseval's relation. Now, we want to compute the average, ensemble averaged power by taking the expectation of this random variable and also let t tend to infinity. So here goes the definition. And this is the definition of the power of a random process. See that? This is the definition of the ensemble averaged power of the random process, which involves time average too. So see that? Let t tends to infinity. And you have the expectation of the instantaneous power of the truncated signal. So you have the limit, you have the expectation, you have 1 over 2t, you have the finite interval of x of t. And we can rewrite it like this. And here goes what? Hey, this is nothing but the time average of expectation of x of t squared, which is what? Instantaneous power of the random process. So we can write it as what? Capital A of capital E of absolute value of x of t squared. Of course, this part can be replaced by our well-known notation, R sub xxtt. So autocorrelation evaluated at t and t. So this is the power. Now, what is left? Probably we want to define power spectrum. Means that we want to find some frequency domain equivalent, which is integration in the frequency domain of something. And we want to define that something as power spectrum because it gives us the power, right? So here goes the definition of power spectral density. This is the definition. Why? here goes the derivation. So I copied. Average power is simply can be written as this one. And using Parseval's relation, you have this one. Now, let's take out integration and put limit. And what happens? Average power is the integral of what? A frequency function. That is very interesting. See that? You truncate in the time domain, and you find the energy spectrum, and you take the ensemble average of the energy spectrum, and you divide by 2t, and consider the limit. If this limit converges for every f, this is called the power spectral density, and its notation is sometimes S spectrum subscript XX of F. The reason why, again, we have two subscripts X is that we are going to define cross power spectral density when we have two random processes. So we will have S sub XY, P sub XY, cross power spectrum, something like that. So again, here, see that power is integration of the power spectrum. And the reason why this is fully justified, this name, is related to what? Again, the filtering of the random process. So you have random process, X of t, and LTI filtering, and you have Y of t. And probably what you want to see is that average power of the output is what? In the frequency domain, you have some result like this. Actually, this will be derived, but unfortunately not today. And you can find that in standard undergraduate textbook and graduate textbook. But anyway, this justifies really this function defined as this one is the power spectrum. Anyway, so remember the definition. The reason why I emphasize the definition is this one. I also, even though I studied the people's book using it as a textbook, and many professors, even many researchers, they were given the definition of power spectrum. They forgot. They forgot and just remember the theorem. That is Wiener-Khinchin theorem. It's a way to very easily compute the power spectrum. But the problem is that some textbooks, in order not to ward off those students, they just use the Wiener-Khinchin theorem's result as the definition of power spectrum. That is very, very misleading because your, for example, spectrum analyzer as an RF engineer or communication engineer you will use actually is based on the definition, not the Wiener-Khinchin theorem. Okay? So what they do is that they take samples and truncate it and put some window and do just Fourier transform, fast Fourier transform. And then they take the absolute value and they do some kind of time average. Got it? So without realizing this is the definition of the power spectrum, you may have some problem. Another thing is this one. Sometimes we want to remember properties of power spectral densities. Some properties of power spectral densities are very easy to understand if you remember the definition. But if you use that strange definition based on the Wiener-Khinchin theorem, then you may suffer a lot to prove very simple result. Okay, so please remember the definition and also the theorem, Wiener-Khinchin theorem. That is the topic of next section. But before, our textbook has the example. So see that this random process what has each sample pass power signal because it's a sinusoidal signal, right? If you fix A and theta, it's an infinite energy but finite power signal. Now, let me ask you, what would be the power spectrum of this one? What should it be? Because it has sample passes all cosine functions with the same frequency. So what you want is that, hey, if our definition is well defined, what do you guess? At F0, you have some delta function because no other frequency component exists. But integration of this function must be a finite power, right? So we must have delta functions located at F0 and negative F0. The problem is that what would be the proportionality constant? And we believe that, okay, the constants must be the same. And if we integrate this one, it must be the power of the signal computed in a time domain. And we remember what is the power like this. And after average, we have that. So, hey, I guess the proportionality constant is this. So if we add this one and that one, then, makes sense, right? Now let's see. By using the definition, let's compute the power spectrum. The problem is that it's not easy to compute the Fourier transform of truncated sinusoidal signal. If you truncate in order to house exact integer multiple of period, then it would be okay. But if it is not, as you have done in your high school math, it's complicated, messy function. But anyway, you can show this, as I told you. Now, this one of the simplest random process has problem when you apply the definition directly to compute the autocorrelation function. Definition is good, but hard to use. Then what do? You find some theorem that says that this theorem provides alternative way to compute autocorrelation, power spectral. That is the Wiener-Khinchin theorem. Ready? So let me skip the properties of power spectrum. If you remember that definition, see that this is a function of f, and this is what? Absolute square expectation. That is non-negative. Limit is non-negative. So it's obvious, right? But it's not that obvious if you start from the Wiener-Khinchin theorem-based definition of power spectrum. But if you use this definition of definition, or a definition of the power spectrum in terms of the truncated version, it's obvious. First property is just obvious. Whether X is real or complex, see that your Fourier transform, magnitude square of the Fourier transform appears. So it's always non-negative, whether X is complex or not. It's always real non-negative function of F. And you can also show that if the function is a real function, then due to the property of the Fourier transform of a real valued function, you have this result, symmetry of the power spectrum. And some other things. And the last one is this one. Last one is actually the Wiener-Khinchin theorem. See that? Power spectral density of X is what? The Fourier transform. This is Fourier transform of what? Time averaged autocorrelation function of X evaluated at t plus tau and t. So two parameter function you have. Now let me ask you a question. This average is with respect to which parameter? T, okay? Never forget this. Time average is over the parameter t. So after you average this two parameter function, you have a single parameter function of tau. So your Fourier transform is with respect to the parameter tau, not t. Okay? And then your result is a function of f. Actually, this 6 is what? The Wiener-Khinchin theorem. So anyway, if the random process is wise and stationary, then something better appears because power spectrum is what? the Fourier transform of the single parameter autocorrelation function. And from Fourier power spectrum, you can find the autocorrelation function. But be careful. Suppose you are given an power spectral density of random process without knowing the random process is Y-stand stationary or not. Then what would be the inverse transform of the power spectrum? That is what? Time averaged autocorrelation function. Okay? In general, never forget that. Next topics are about the bandwidth of a random process when X is a baseband signal and X is a bandpass signal. But let me skip that one. We may have to talk about this again in some digital communications course. Okay, let me skip. So here goes the theorem. So entire section 7.2 is about the Wiener-Khinchin theorem. That is about the equivalent way to find the power spectral density. So the Wiener-Khinchin theorem says that, hey, using the definition to find the power spectrum of a random process would be too difficult. Why don't you use this way, which exactly gives you the idea? So remember that. You compute the autocorrelation function of X as a function of T1 and T2, but replace T1 as T plus tau and T2 as T. And then you take the time average with respect to T. Then you have a function of tau. Its Fourier transform is the power spectrum. Got it? See that? First, you compute the autocorrelation. You average with respect to T. And then you have the Fourier transform relation. The derivation is a little bit complicated, but you can do that if you keep the conjugation and negative sign properly. Okay, so I'm just showing you how to derive, but I will not line by line tell you. But anyway, what is important is this one. Time averaged autocorrelation function of the random process parameterized by T plus tau and T is the Fourier transform pair of the power spectral density. Sometimes this simplified Wiener-Khinchin theorem for Y-stand stationary random processes are used even the definition of random process. I'm actually very shocked by those authors. Too bold to attract the students to their department. Anyway, so now let's revisit our problem with what? X of t equals some random variable times cosine 2 pi f0 t plus uniform. We had a difficulty to use the definition. Now, let's start from the autocorrelation function we already know. Let's Fourier, since this is a function only of tau, by just taking the Fourier transform, we have the same result. Now, let me ask you, are you going to use the definition or are you going to use the Wiener-Khinchin theorem? Of course, both of them, right? But depending on the situation. So you have two tools in your toolbox, definition-based tool and Wiener-Khinchin theorem based tool to find your random processes power spectral density. And here goes an example. So autocorrelation function is triangular. Then what is its power spectrum? We know that triangular function is what? The convolution of two identical rectangular pulses. And we know the convolution theorem from signal-gen systems. In the Fourier transform, frequency domain, they are multiplied. So sinc pulse squared is the power spectrum of the this random process with triangular autocorrelation. Now we can do the same thing for the cross power. Then let's define what is the cross power. So consider where a random process is summation of two random processes. So see this, W is equal to X plus Y. Now let me ask you a question. What is the power of W? Is it the sum of power of X and power of Y? You know it is not, because this question was asked in your circuit theory course, right? You remember that, right? You cannot just simply add 2 power to have the total power, because 2 signals may affect each other through what? Cross power. So let's compute the autocorrelation, which is a generalized version of cross power, because instantaneous autocorrelation can be found by setting tau equals 0. You have 4 terms, right? And power of x and power of y only explains 2 of the terms. What about other terms? They are called cross correlation function and related to the cross power. And if we Fourier transform after time average, we will see that power spectral density itself is also not the summation of 2 power spectral densities, but we have 2 more terms. What are they? They are going to called cross power spectral density. And simply XPSD. X means cross in most of the definitions. And derivation is almost the same. So it's the generalization of the definition of power spectrum over single random process. Instead of using x and x, we use x and y after time truncation. So here goes the truncation of x random process, truncation of y random process, and their Fourier transform pairs. And then we find the cross power inside the finite interval. And then we take the ensemble average and we take the limit to define what? Cross power. So cross power is simply that one in the frequency domain, and this one, this one in the time domain. So this is time domain and this is frequency domain. Now we want to define the cross power spectrum. So what? We take the integrand and say that this is the cross power spectral density. And again, by filtering x and y, we can show that this really means cross power contribution of 2 signals at specific frequency f. So it really makes sense. Anyway, we have similar properties of cross power spectrum, and you read it yourself. And we also again have what? The generalized version of the Wiener-Khinchin theorem. So instead of using the definition of the cross power spectrum in the frequency domain, why don't we use the Wiener-Khinchin theorem generalized for cross power? The result is very simple. Now, instead of considering the autocorrelation function, you consider the cross correlation function. And you take the time average with respect to t. And then you calculate the Fourier transform to find the cross power spectrum. Got it? And if the random processes x and y are jointly wise and stationary, we don't need time averaging because our cross correlation is already a function of tau. So it's not a function of t, so its time average is itself. So we are done. And now, I'm too fast, but we can generalize, we can modify our definitions for continuous time random process power spectrum, cross power spectrum to discrete time cases by using discrete time Fourier transform. We can do that. And it's very simple. Just we use time average using that one. Okay. So exact parallel result we have. We have Wiener-Khinchin theorem. We have all the other stuff. Got it? So let me skip. Yeah. Now, this is actually very important part in the Peebles book, because he was a radar engineering professor, and additive white Gaussian noise was one of the most important noise model for undergraduate students. And the problem is that we need to define white noise because there exists some noise process in the RF component. What is that? In the receiver or receiver of the radar part, after transmit, it receives, right? We have a so-called low noise amplifier. Anyway, our signal is too weak to drive our circuit, so we amplify the signal. The problem is that every non-zero Kelvin degree material has what? Its components have thermal jittering. And due to the thermal jittering, our electron that passes through the conductor has what? Has some problem. It's not superconductor. So we have bumping around of the electron, even though it has mean velocity. And that is amplified and observed by the receiver after amplification. And this thermal noise can be in the frequency domain well modeled as a almost flat spectrum signal. But since there is no infinite power signal, our power spectral density of real world noise is flat, and it decays if our frequency goes up. But if our application observes that one in a very narrow sense, we can just mathematically model that the power spectrum is flat. In that case, what happens? This is the power spectrum. And its Fourier transform, inverse Fourier transform, which is the autocorrelation, time average autocorrelation, becomes delta function, which means that sample at t. And if you just take a small offset, two random variables are orthogonal. Okay, something like that. And this really appeals our previous definition of white noise in the time domain. You remember that Q of T1 times delta of T1 minus T2 as the autocorrelation function? Same thing. Anyway, the textbook explains using physics why this happens. You know, not only Kelvin, some Planck constant, blah, blah, blah. I almost forgot. But this part must be covered in some communications courses. So let me skip. Also important thing is the power spectrum of complex processes. And this is also deferred to some advanced graduate courses. So in this way, we covered chapter 7, covered the most important topics. Unfortunately, they are not all. Our populist book, chapter 9, in the first part, it introduces more definitions related to random processes. For example, cyclostationarity, which I really love as a researcher, because many man-made signals in communications or sensing can be classified as cyclostationary random process. Anyway, those definitions and some properties are all not covered, but you can find the link of video lecture and the handout from our this year's homepage, because I Control C and Control V already. Okay, so if you are interested after the final exam to further know that, just view those things, and it will greatly help. Anyway, good luck in the final exam. Okay, that's all.